digital version. And the digital measurement instrument, they are the ones that will process a signal and produce a result in discrete form, not continuous form as in analog. Most of the natural signal, they occur or they are in analog form. So because of the many advantages that digital system has, we convert it into discrete form, then process it and bring out the result. And some of these advantages of the digital instrument are: the first one, it can detect a signal of very low level. It is better than analog in that respect, and it has high input impedance. And what that means is that the amount of current to be absorbing is very small, therefore there is less problem of loading effects. And the low power consumption is another advantage. High frequency range is another advantage, and better resolution is another advantage. Resolution, as we all know, is the clarity of the display. And the storage facility, the digital has storage facilities, unlike the analog, which don't. And of course, the last thing is they are highly accurate. The accuracy of digital signal is better than that. Measurement instrument is better than that of the analog. What are the disadvantages? Because we don't have any system that will be 100% correct. The first one, it is suffering from the effect of low noise, unlike that of analog, which is very low. Second disadvantage is that the analog instrument, they have higher overload capacity. When the analog is highly overloaded, it cannot be damaged, unlike the digital, which don't tolerate that. And another disadvantage of the digital is that the instrument sometimes will give you unreliable reading, and there are two causes for this. Either one of the electronics components in the digital system is faulty, or the display is damaged. So in any of those ways, you can have an erroneous signal, that is the signal or the reading which is with low reliability. And the last one is that the digital instruments and the internal circuitry or their internal component, they are very much sensitive to changes in environmental factors. What we mean here is that whenever temperature increase or the pressure increase, definitely that affects the reality, the correctness of the result given by the digital instrument. The next thing we do is to look at the performance characteristics of the digital instrument. What are those properties on which we judge whether the instrument is working nicely or not? The first one is resolution, and this resolution is nothing but the smallest increment in the voltage that can be detected by the digital measurement instrument. And for us to make it very clear, the resolution is defined as the smallest increment in the output voltage, which is determined by what we call the least significant bit. If you have any number of bits that is a digital display, you find that the first one from the left is most significant bit, and the last one on the right, we call it least significant bit. So this resolution is expressed in percentage. Resolution is equal to 1 over 2 raised to power n minus 1 times 100, that is in percentage, where n is the number of bits. It can be 4 bit, 8, 16, 32, like that, powers of 2. The next thing that we use for characterizing the digital measurement instrument is the accuracy. And the accuracy, as we have already seen from our lecture number 1, is the actual output given by the instrument with respect to what? The expected one. The difference between the two is what we call the accuracy. And this accuracy, mainly, it is expressed in a percentage of the what? Total reading that the instrument can give. And in ideal situation, the accuracy of any digital measurement instrument is expected to be within plus or minus half of least significant bit. For instance, if you have an 8-bit converter, the least significant bit will be equal to 1 over 2 raised to power 8 minus 1, and that will give you 1 over 255. And if you multiply it by 100, it will give you 0.39% for the full scale of the measurement ability. And the 8-bit, for instance, if you have an 8-bit, if you say 1/225 and you multiply by 100, it will give you 0.39%. And the accuracy of any digital measurement instrument is expected to be not more than 0.2%. And the next thing, what is the next property or the next characteristic that we use for classifying the operation of a digital instrument is what we call linear error. Remember, in my first lecture, I told you what is linearity of a system. I told you a system is said to be linear if it fulfills two necessary conditions. The first one is homogeneity and the second one is additivity. So if you say a system is linear, it means whenever there is a given increment in the input, so we expect to have a corresponding or proportional input, level of increment in the output. That is to say, the relationship between the input and the output is supposed to be a straight line relationship. The next characteristics of categorizing the operation of digital instrument is what we call monotonicity. And if you say something is monotonic, what it actually means is that there is no reverse. So the fourth characteristic of a digital measuring instrument is monotonicity. If you say a system is monotonic, it means once there is a proportion relationship between the input and output, you cannot have any reverse step. That is, supposing we have 3, 4, 5 measures in which they are proportional to one another, it is not possible for the 6th or 7 or any other one to be in the reverse direction. They always move in the same direction. And the next characteristic is what we call the settling time. You see, whenever there is a change in the input, we expect ideally to have an immediate change in the output, but in reality, this is not what happens in practice. Whenever you have a digital to analog converter, it will take some time before the new output will settle to the final position with respect to the new input. And the settling time is defined as the time it will take the digital to analog converter to settle within plus or minus half of its least significant bit. And for us to understand this better, let us look at the graph that is showing the nature of the settling time. As you can see from this graph, this is the vertical axis, which stands for the value, and this is the time axis. So from the origin, when it starts, we assume we have an initial value, that is, it is not starting from the origin. So as you can see, first of all, it will shoot above the final settling value, and it will keep on oscillating above and below that before it finally came within the bracket of these two lines, which are within half of the least significant bit. The upper one plus and the other one is minus. So the time it will take from the origin to reach this point where the value is within half of the least significant bit is what we call the settling time. And another characteristic of a digital instrument is temperature sensitivity. As we all know, most of the measurement instrument, whenever the temperature, the pressure and other environmental parameters change, it is also being affected. That is, their behavior is being affected. So the digital to analog computer, it is very sensitive to temperature, and for this reason your output voltage will depend, of course, to some extent on temperature, because the temperature do affect its value. So the range of this temperature sensitivity for digital to analog converter is within the range of plus or minus 50 to plus or minus 1.5 per degree Celsius. So with this, we now start looking at the first digital instrument, and this is what we call digital multimeter. The word multi, it means it can measure different parameters, and for this, the digital multimeter can measure DC voltage and the DC AC voltage. It can also measure DC current and the AC current, and of course it can measure resistance. This is the block diagram, as you can see, this is the point at which our input is delivered, and here is like we have a selector. If I turn it to connect with this, it means I'm measuring resistance. If I connect with this, I'm measuring AC voltage. With this, AC current. With this line, I'm measuring DC current, and the last one is for the DC voltage. And whenever you are measuring any parameter which is not DC voltage, meaning all the orders, DC current, AC voltage, and resistance, whenever you are measuring them, then the first thing that is done, we convert that your parameter into equivalent DC voltage, then it will now carry out the operation. Now, from this diagram, as you can see, if we want to measure AC voltage, the input is now delivered, is fed to the calibrated compensated attenuator, as you can see from this diagram. For measuring the AC current, it has to pass through through this calibrated attenuator, after which we now change it into a DC, because this is what AC to DC converter, and the output of this is now delivered to ADC, so that we can change it from analog to digital and finally display the result in that form. And if you want to measure the current, for instance, there will be a drop across the internal calibrated shunt, as you can see from this diagram. This is my shunt for AC current, and of course this is my shunt for DC current. So for each of them, if it is AC, it has to pass through AC to DC converter, but if it is a DC current, this will pass through a shunt, which will go to the ADC, that is analog to digital converter, and finally to the display. Now, as I've already said, there will be a shunt whenever you are measuring a current, and that current will now pass through a shunt, as I've explained, and it will now be converted into DC before it is now changed into analog, from analog to digital, as we have already seen from this diagram. Now, the accuracy of this kind of digital multimeter is ranged between 0.2 to 0.5% of the full scale. And whenever you are making a measurement, you should know that its accuracy, if you want to get an accurate result, it should be within the range of 50 Hz. Because whenever you are measuring any frequency lower than 50, there will be fluctuation in the value that will be displayed, which represent inaccuracy. And if you are measuring at frequencies which are higher than 50 Hz, then we have a deterioration, that is reduction, that is degradation of the ADC, analog to digital converter. It will not have good accuracy, and that will affect the overall accuracy of the measurement. What we are saying is, for you to get a best result, the frequency of your measurement should be 50 Hz. And whenever you are taking AC measurement, so the reading that will be displayed, it should be RMS, that is root mean square, and sometimes it can be the average value of the unknown current you are measuring. Now, the next digital instrument is what we call frequency meter, and this is an instrument that we use for measuring the frequency of any periodic, that is AC alternating waveform. And of course, the principle on which it acts is we take that our periodic signal, we pass it through a gate, and that gate will be the one that will be receiving the pulses from the alternating source with respect to our clock, and the number of pulses it detects or it accepts is now going to pass through an AND gate together with the clock. This is a type of what we call synchronous logic. In this way, whatever is delivered as output from the AND gate should now go to the counter, and the counter will now tell us the number of pulses from our original periodic input, and that count number will be equal to the frequency of the periodic waveform, and that will now be decoded or displayed on our screen. For instance, if our signal is taken within 1 second, so the number of variations within that 1 second stands for the number of or for the frequency for that signal we are trying to measure. As you can see from that diagram, we have a counter or decoder, we have a clock, which is our oscillator, we have a divider, and we have an AND gate. The function of this counter, it is made using BCD counters, that is binary decimal coded or binary coded decimals. So the display or the decoder on which our result is presented, it is the unit that will now convert this BCD into typical decimal display. And the gate, as I told you, is used for us to know the number of times there is a variation in the periodic waveform, and the source of that periodic, as you can see from here, it will pass through an attenuator to make sure that it is within some limit so that it cannot damage the whole system. And on the other hand, we have our clock, which is generating the controlling pulses. So the two should be available before the AND gate should give us a high output, and whatever we get will be passed through counter to detect the number of variation in this our original signal, and finally it will be displayed on the screen. Now the divider circuit, as I said, is the one that is serving as one of the legs of the input. As you can see from this, one of the legs of this AND gate is from our divider, and the other one is from our Schmidt trigger, which is from the original source of signal whose frequency we want to measure. So whatever is the number of pulses that are detected from the output of that AND gate within a period of time, we now say that is our frequency of the alternating signal. So the next device under this digital instrument is a digital voltmeter, and this digital voltmeter, as you can see, it is for measuring voltages. And of course, although it is digital, it can measure AC and DC voltages as discrete numbers. That is, it will take the AC and DC, but the results should be in discrete form. And of course, this digital voltmeter is used in many laboratories and other applications that deals with the voltage, either AC or DC. And because of the development in the ICs, that is integrated circuit, with respect to the reduction in their size, with the reduction of their power consumption, and of course this leads to the reduction of their cost drastically. And the block diagram of this digital voltmeter, you can see it here. We have our non-input voltage, which is delivered to pulse width generator, which will be generating some pulses, which are the width of that pulse is directly proportional to the amount of the voltage we are measuring, either AC or DC. So the output of this pulse generator will now be applied to the AND gate. One of the legs of the AND gate, as you can see here, is my AND gate, while the other one is supplied with direct trigger pulses, which are positive in nature. So the two will now serve as input to our AND gate, and of course this will give me pulses which are also positive. But because we want to deal with the negative, for the reason we have to pass it through an inverter, and our pulses or the trigger pulses have now changed from positive to negative, and these pulses are now passed through counter, and the number of counts is directly proportional to this our input unknown signal, and of course it will be sent to a calibration system, which will now display the actual voltage of the power we are measuring. So if you look at this, then the digital voltmeter we discussed here, of course it is just like an analog to digital converter, and for this reason you can use any type of ADC to come up with the digital voltmeter, because the principle, as you've seen, is just like changing analog into a digital. So we have different types of digital voltmeters depending on the type of analog to digital multimeter, converter we use. And in summary, this is the block diagram. The input signal goes to attenuator, and the output is now passed to ADC to change from analog to digital, and the output of this one is passed through a counter that will give us pulses or the count proportional to the size or the magnitude of this input signal, and it will now be displayed following a given standard scale. So these digital voltmeters, they have different applications, but the most common area of the application is in data processing or data logging. What we mean by data processing is a situation where you have a system that produces continuous signal. So you want to be capturing that signal after maybe a certain period of time. So whatever it captures, we cannot pass it through this ADC so that we can take it to a system to analyze or maybe print it out. And the data logging is the same thing. It's something that will be monitoring a particular system, taking readings from time to time. So the number of analog signals that we are detecting from either this data processing or logging, they are now scanned sequentially, that is after a fixed period of time, and then these signals will be converted into equivalent digital value by using ADC in the digital voltmeter we have seen. And this digital value is then transmitted. It should be sent to an information system where we will be recording what we are seeing from the system we are monitoring, and the whole data that is collected from that system and converted to digital form can be printed, or it can be logged, that is stored in a storage memory for further use. So the large number of data can be actually captured from this kind of systems in such a way that a person, human being, cannot stand and do it correctly, but this system can be capturing and storing it for our future use. Now the next thing is we look at transducer, and the transducer is a device that converts one type of energy to another. Basically, in this respect, we are talking of the device that can change any form of signal to either electrical or to mechanical form. But because we are looking at electrical measurement devices, we are concerned with those devices that will capture energy from one form into electrical form. And of course, the energy, it can be electrical, it can be electronic, it can be electromechanical, it can be electromagnetic, it can be photonic or photovoltaic. That is, energy from all these systems can be changed into what? The real electrical form. And we use this transducer in many measurement systems, including the measurement of information transfer. For instance, if you want to measure pressure from a particular sensor, if you want to measure temperature from a particular system, all these we can use a transducer that will capture those physical signals and give us a result in electrical form. The term transducer is used in two senses basically. The first one is the one we have just discussed, the one that will detect a parameter from a particular any form of energy and now change it into electrical signal. That electrical signal can be analog, can be digital. This is the one sense of what using the term transducer. The second one is the one in which the audio speaker will now convert the electrical energy passing through a wire delivered to it, and it will change it into vibrations, and these vibrations will now produce a corresponding sound, that is changing the electrical signal into what? A sound energy. We use this term, a transducer, to represent this also, but the main concern of this course is the first one, that is any device or any sensor that will capture signal in any form and present it in electrical form. Now the electrical transducers are defined as those transducers which convert one form of energy into electrical energy for measurement purpose or for any operation. And the quantities, the parameters which can be measured, can be a pressure, it can be a displacement distance, it can be temperature, it can be humidity, it can be fluid flow, it can be any other form of energy, but it will now be changed into what? Electrical form. So these signals are required to be sensed, that is, they have to be detected by a sensor, and that sensor is actually our transducer. Then it is the one that will produce a proportional signal that will be changed into electrical form equivalent to the pressure, displacement, or anything we have measured. Now, what are the advantages of electrical transducers? The first one is the power requirement is very low. Electrical transducers consume very small amount of energy to detect energy in one form and change it into electrical or electronic form. Then the second one is it has an advantage that we can use an amplifier whenever the level of the original signal we are detecting is very low. We can use electrical amplifier to boost it so that we can accurately detect it. And the third advantage is the noise effect, which is very small in these electrical transducers. And the fourth one is the mass inertia effect is very minimal, because as we have said, we are detecting signal from any other form, pressure, temperature, humidity, and it will now be changed into electrical or of course electronics form. And the mass of electron, as we know from our chemistry, is very, very negligible, 1/1850 or 1840 something with respect to the mass of what other atoms. Now the last one, or the fifth one, the output can be indicated or it can be recorded at a very far distance. That is, you can detect a pressure, you can detect a temperature and transmit it wirelessly to a remote point where it can be received and analyzed. Now, what are the basic requirements for a good transducer? For a transducer to be good, it has to have first one, linearity. And the linearity, I have told you that there will be a proportional change between what is detected and what is presented. They have to be what? Proportional to one another. Whenever, for instance, the amount of pressure we are detecting is increasing, the corresponding electrical signal produced should also be increasing. The second one is ruggedness. The electrical transducer is expected to be able to withstand the overload. Whenever it is loaded, we don't expect it to fail easily because it's supposed to have this property of ruggedness. And the next one, which is number 3, is repeatability. The repeatability, as we have seen from our first lecture, is its ability to produce almost the same result for a particular thing that we measured several times. The next requirement for a transducer, it must have a high reliability and high stability. By reliability, we mean accuracy in the result, and by stability, we mean to be able to be stable in such a way that it will not be introducing random errors in taking readings. The next one, which is number 5, is high output signal quality. The signal that will be displayed, it should be very good, far away from noise, in such a way that the quantity of the good signal compared to the noise should be very high. That is, signal over noise should be very high, meaning the noise is very, very small. The next one is number 6, that is no hysteresis. What we mean by hysteresis is, for instance, if you have a soft iron and you apply electricity to it, you can magnetize it. What we expected is that whenever we remove the source of electricity, it will have zero magnetism. But that ability of retaining some amount of that magnetism, even though the source of magnification, electricity, has been removed, so that ability to retain that magnetism is what we call the hysteresis. So we assume all our good transducers, electrical transducers, they should have no hysteresis. Whenever the source is removed, the energy stored in it should be zero. And the last one is similar to the hysteresis, that is residual information or free information. It is the one in such a way that whenever you remove the source from which you are detecting, the deformation on that input or on that material should be zero. It will come back to its original form so that it can take a new fresh reading. So with this, ladies and gentlemen, this is the end of this class. Thank you very much for your attention. I advise you to watch this thing number of times repeatedly so that you can understand the subject better. Thank you.